Well, hello, ladies and gentlemen. We're going to go over the even questions on our mole review for 2018 and 19. So we're going to do 2 through 28. The previous video we did the odds. So let's zoom out here. I'm not going to get the problem set up for you. You'll have to do the math with your calculators to get them all finished up. I better zoom out a little. Okay, so question number 2, what is the molar mass? Molar mass is grams per mole. You find it from looking on the periodic table of the following. So you got to take a look here at iron, and iron is 55.8, so 56. But there's 2 of them, so 2 times 56. Plus, we have 3 oxygens. Each oxygen weighs 16 grams per mole. So at this point, you can do your own math. I'm not going to do it for you. The answers, though, will be grams per mole. Because the atomic mass units we see on the periodic table atomic weights, they directly convert into grams per mole when we have Avogadro's number of the element. That's kind of cool. Over here, we've got the same thing going on. We've got, oh, I didn't have to go that far over. So we got calcium. So you look on your periodic table. Calcium has a weight of 40. There's just 1 of them. And we've got oxygen. Its weight is 16. Let me verify that. Yeah, 16. And we've got 2 of them, so I'm going to multiply that by 2 because this subscript 2 is telling us everything in the parentheses. We got to multiply by 2. Plus we have hydrogen, which weighs 1, but we have 2 of them. So 2 times 1 of them. So you can do this. It's going to be 40 plus 16 times 2 plus 2. You can get that. Okay, moving on to number 4. How many moles are in the following? Let's see. Scooch that up. Maybe I'll adjust this here. Sorry for the bumping. You know what? I'm going to make a little mole MVP table here. Mole is the most valuable player of chemistry. And let's see. How many moles are in the following? So we want to end up at moles on this problem, and we're starting at grams. So the M stands for mass, which is measured in grams. And so we're going to put we got our given over 1, so that's going to be 24 grams. Now anytime we're going from the outside of the triangle, or if you prefer, anytime we're calculating moles, we're always going to be dividing. Anytime you're going this direction from grams to moles, you're dividing. Or if it was molecules to moles, you're dividing. So we're going to divide by the molar mass of this chemical. So that means if we're dividing by the molar mass, we put 1 mole on the top of CH4. And how many moles? Let's see. Oh, we need to know how many grams. Grams of CH4. Well, carbon is 12. Each hydrogen is worth 1. So we've got 16. There you go. You can do your own math on there. It'll be a little bit over 1, it looks like. Okay, so for this one, similar setup. We're starting at grams over here, so that's our given. And this is carbon monoxide. You might have heard of that. It's a form of carbon monoxide. It holds on tighter in your blood cells, so if you get a whole bunch of this in your blood, it's very hard for it to be released, and so it can be very damaging. Anyway, we don't care about that. We want to divide by the molar mass. Carbon is 12, oxygen is 16, 6, 7, 8, and I think that's going to be 28. That's 28 grams of CO is 1 mole of CO. The grams cancel out, and then with your calculator, you'll just divide those out, and that'll tell you how many moles you have of that. All right, number 6. Okay, with number 6, how many moles? So we're looking just like we were up here. We want to end up at mole, the middle of the MVP triangle. But now we're starting up here at liters. So we're starting at liters at the top. So you're going to have to, once again, since we're going from the outside to the middle of the triangle, we're calculating how many moles. We're dividing. So we're going to take the given, put it over 1. Then we'll do our dividing over here. And the magic number that connects moles to liters is 22.4 liters of a gas at standard temperature and pressure. We'll have 1 mole of elements, Avogadro's number. So we're going to divide by 22.4 liters of C3H8 is 1 mole of C3H8. The liters cancel out, and now it's just going to be dividing those two numbers for you. This one over here, same idea. We're still starting out here at liters, and so we're going to divide by the molar mass. This is just a one-step conversion here. I think all of them on this page are one-step conversion, so the given over 1. And let's see, 22.4 liters of NO, any gas, will be 1 mole of NO2. So that's kind of neat. So if the gas is at standard temperature and pressure, which we will always assume. So now it's going to be 448 divided by 22 will tell you how many moles you have. All right, let's jump over now to the next page. All right, so number 8. Get that centered for you. I can zoom in a little bit more maybe. All right, how many atoms of hydrogen? Okay, so we want atoms of hydrogen. So we're going to, before we can figure that out, we got to realize that in this one molecule of this gas, this is C3H6, this is going to be propane. So every molecule of propane, we've got 6 hydrogens. So I'm just going to write that over here because it's actually while we're going to end it. So there are 6 hydrogen atoms per or for every molecule of C3H6. 1 molecule C3H6. Now this is how we're going to end it because we know that every molecule has 6 hydrogens. Well, now we just got to figure out how many molecules. And so if we're given this many moles, molecules are down over here. We need to multiply by Avogadro's number to figure out how many molecules we have. Oh, and look at right there. I've even got this. And then we're going to multiply it by how many atoms per molecule. That's supposed to be molecule there. So our given 0.75 moles of C3H6 over 1. I like putting that over 1 so you don't put anything underneath there. Now we've got to convert it into molecules by multiplying by Avogadro's number, just like we've been practicing. So 6.02 times 10 to the 23, and this is going to be molecules, molex, of C3H6 is 1 mole of C3H6. The moles cancel with moles there. So now you're going to enter in your calculator, oh, that's a decimal point there, 0.75 times Avogadro's number times 6. Now this one over here, you're going to set it up just the same way. Let me scoot that back so we can see it. So, but now, except you've got 2 moles, so that's your given, 2 moles of C5H10 over 1. Okay, the same step's going to be, you're going to do the same thing here. You're just going to take Avogadro's number, but then at the end, we got to multiply it by how many hydrogen atoms are there in 1 molecule of this. So let's see. Well, there's 10 hydrogen atoms in 1 molecule of C5H10. So you're going to have Avogadro's number there times 10 to the 23 molecules of C5H10 is 1 mole of C5H10. So let's see. The moles cancel there. That's good. That lets us know we set this up right. The moles of C5H10, that was supposed to be molecules. Sorry, my bad there. Cancels there. So now it's going to be 2 times Avogadro's number times 10. Number 10, what is a mole? Well, technically it's 6.02 times 10 to the 23 of whatever you're talking about. It's a number. It's a huge number. It just happens that for chemistry, that's 6 protons. So 6.02 times 10 to the 23 protons equals 1 gram. And that's how they kind of came up with this, because protons are kind of a big deal in chemistry. It's really, when we look at these atomic weights, every one of those numbers there represents the weight of a proton. And let's see, what is the molar mass? So the molar mass lets us know how heavy it is if we have Avogadro's number of that chemical. So molar mass is the grams in 6.02 times 10 to the 23, either atoms or molecules, depending upon whether you're talking about an atom or a molecule. So it's just how many grams, and we tend to measure that in grams per mole. And a mole is just a big number, but it turns out that 1 gram of protons is exactly Avogadro's number. Let's see, a mole is equal to, okay, these are our 3 things that we're either multiplying or dividing by: 22.4 liters, 22.4 liters, or Avogadro's number of particles, 6.02 times 10 to the 23. We've been working with that till we're blue in the face. And, okay, this is molar mass, okay? Molar mass, which is grams per mole, which is where that is, okay? So that's what we're looking at there. Right, moving right along here. Number 14, what is the mass of 1 mole of carbon? Well, the nice thing is, because we talked about it over here, that the molar mass and the atomic mass, they are the same numerically. They have different units, but you can directly convert atomic mass units to grams per mole. So what's the mass of 1 mole of carbon? Well, 1 carbon atom would have a mass of 12 atomic mass units, but if we're talking moles, it's going to have 12 grams per mole. So the mass of carbon is going to be 12 grams per 1 mole. Now, we put grams per mole. We could actually put the 1 mole there. We just usually don't bother to do that. And what is the molar mass of CO2? Well, let's see. We know that the carbon's mass, if you have 1 mole of that, it's going to be 12 grams per mole. Then we've got oxygen, and we got 2 of them, 2 times 16, because when you look on the periodic table, the molar mass of oxygen would be 16 grams per mole. But we have 2 of them, so it's going to be 32 grams per mole. When we add these 2 up, because they're in the same compound, it's going to be 32 plus 12 equals 44 grams per mole. Please tell me I did not go off the slide. I did not. Okay. Okay, coming on over here. How do you set up a conversion? We've been working on these ever since the first week of school. And the conversion, you got to first read the problem, find the given. It's the number that you got to change. And I recommend you put that given over 1, because then what you do with the conversion is now you're going to multiply it by 1 or more conversion factors, which we're going to put in a fraction form. It could be 1 mole is 22.4 liters. Okay, on there, the conversion factor could be 1 mole, which we can put down here as 6.02 times 10 to the 23 atoms. Okay, so we've got these. So you've got the given over 1 times 1 or more conversion factors. And you know you got your conversion factors set up right if you can cancel these off. Since this is liters, our given must be some number of liters there. So that's how you set up a conversion. The given over 1, multiply it by the appropriate conversion factors. Okay, number 18, rearrange the molarity equation. Well, molarity equals moles divided by liters. That's a base equation. We'll give that to you on the test. I am a big fan of equation triangles because they're just fun. Moles over liter. Well, okay, not fun, but they make your work a lot easier. Moles over liter is molarity. These you'll multiply, those you divide. So moles, if we cover up moles, here's why equation triangle is so cool. The equation for moles is molarity times liters. Molarity times liters. Liters, if we cover that up, now you can rearrange this algebraically, but this makes it quicker. Moles divided by molarity. Moles over molarity. You always start from the top and read down. So you got moles over molarity. And then molarity is moles over liter, which we can see right there in the units. Moles divided by liters. Now, you need to be able to very quickly be able to change milliliters into liters. And you do that, milliliters divided by 1,000 equals liters. So if we divide this by 1,000, you're going to get liters, and the quickest way is to move the decimal point over 3 places. 1, 2, 3, 1 liter. 1, 2, 3, 0.500 liters. 1, 2, 3, 0.100. You really don't even need to put the 2 zeros. And then be careful when we have like 50. 1, 2, 3, you got to add a 0 in there. 0.050 liters. Make sure you got this, because these aren't that tough as long as you're looking at the big picture. But usually we're not going to give you moles. We're probably going to give you grams of some chemical, and then you're going to have to convert it to moles. Or we're going to ask you to find how many grams, so you're going to have to calculate moles. Well, I think we're going to get to that here in a moment, so let me not get ahead of myself. Number 20. Molarity is always expressed in units of moles of solute. That's the solid part. You don't really need to worry about the fancy name. To the next unit. Over liters of the solvent. That's the liquid part. But it's moles over liters. So when you're doing the molarity equation up here and over there, like see right here, you have to make sure you change milliliters to liters. And we did in this one. Number 22, what is the number of moles of solute? So we're looking for moles. We've got 500 milliliters. Okay, we need to change that to liters by doing 1, 2, 3, moving the decimal point, 0.500 liters. Good, now that's what we can use. We know the molarity right there. So going back to our molarity triangle, molarity is moles over liter. We're looking for moles, so I'm going to cover that up. And it's going to be molarity times liters. So moles equals the molarity times the liters. We know the molarity is 0.5. Now I'm not going to put the capital M, I'm going to put the units, moles per liter, because that's just the way I am. Times liters. Duh. Okay, hold on a second. Oh, where's my little eraser deal? Well, I guess I can't find it because I misplaced it. Darn it. Oh, there we go. Sorry. Where were we? I made that too big. That's 0.5 liters. So what's nice is the liters cancel out, and it's 0.5 times 0.5 tells us how many moles, and that's what we're looking for. We're done. You can do your own math. Okay, question number 24. What mass of sucrose? So that's grams, and there's the equation for it. Now, fortunately, we've used this quite a bit in our labs, and I'm just going to say it's 342 grams per mole is the molar mass for this. We've already calculated this several times in starters. There it is. So let's continue on. Let's see if this is a molarity problem or a a mole problem. Is needed to make 400 milliliters, 1, 2, 3, 0.4 liters, okay, and we got a molarity there. So this is a molarity problem. So let's see, the first thing is we want grams, but in the molarity universe, grams don't exist, just moles. So we're going to first find the moles, okay, so then we can change it into grams, and that's kind of standard on these molarity problems. So the first step is the moles equals molarity times liters. And in the problem, the molarity is 0.4 moles per liter. The liters, we adjusted it to 0.4 liters. Now it's 0.4 times 0.4 equals, okay, that's going to be 0.16. The liters cancel, moles of sugar. I'm not going to write that whole thing. I'm just going to put sugar. Okay, are we done? No, we need grams. So now we have figured out wrong chart. We've come to this part. Now we're on the MVP triangle. We've calculated moles using the molarity. We want grams, so we need to multiply by the molar mass. And let's see. Put that over 1. we want the moles to cancel, so 1 mole of sugar is 342 grams of sugar. You can now do your own math on that. Hey, we're almost done with this. Empirical formulas. Okay, well, empirical formulas, the first step. And I'd recommend on our empirical formula homework paper, I put these little notes. You put those on your summary page if that's going to help you. But practice these. We first want to change, we're going to assume that we have 100 grams. Because if you assume 100 grams of the total chemical. Because if that's the case, that means 85.7% of 100 is 85.7 grams of carbon. And then over here, we've got 14.3 grams of hydrogen. So we've just directly converted those into grams. The next step, now you've got to change them into moles by dividing by the molar mass. The given over 1, 12 grams of carbon, you get that from the periodic table, is 1 mole of carbon. That cancels and that cancels. Over here, 1 gram of hydrogen is 1 mole of hydrogen. That cancels and that cancels. So when you do your math, and I guess I'm gonna, let's see, I think I pre-did this. I don't want to take the time now to punch you through. 85.7 divided by 12 comes out to be, what did we get? 7.14. So we get 7.14 moles of carbon. And over here, we're going to end up with 14.3 moles of hydrogen, because those just 1 and 1. So now the next step in this, we're almost there. Now looking at this, you can just tell right now what there's going to be 1 carbon for every 2 hydrogens. But we'll work it out. We're going to divide both of these by the lowest moles we just calculated, 0.714 moles. So now that becomes, for carbon, let's see, that becomes, the ratio number is 1 carbon. And over here, 14 divided by 7.14, well, I can just look at that. I don't need to put it in the calculator. That's going to be 2, equals 2. So this was for hydrogen. So this chemical is going to be carbon 1, hydrogen 2. Lastly, percent composition. So percent composition, it's really just doing what we did there backwards. We've got SnCl2. And let's see, Sn is 119 grams when you look on the periodic table. It lives over here. Let's see, where are we? Sn, there we go, 119. We have 2 chlorines, and each chlorine is 35. We've used that quite a bit, but 35. So that adds up to, when you add up that whole weight, is going to be, when you add those two up, 189 grams per mole. Now when we do percent composition is the part divided by the whole, which means the weight of the element divided by the weight of the molecule times 100. So let's see here. On this particular problem, we're going to have 119 grams of tin divided by 189 grams of the whole compound. You're going to times it by 100 and put that up there. I'm not going to do that for you. Chlorine, we said there was 35 times 2, or 70 grams of chlorine, divided by the whole, 189 grams, times 100. Actually, once you got this percentage, you could just do 100 minus this, and it's going to tell you. It'll save you time on the test. Okay, coming over here, we've got this next one. Make sure we're still in there. I'll zoom in a little bit. Make sure we're centered. Okay, so, I don't know why I had that I there. That was a typo. That shouldn't have been there. Sorry about that. All right, we need to find out how much the whole thing is. We've got 3 times 12, and I think 3 times 12 is pretty easy to do. That's going to be 36 grams. Plus 8 times 1 is just going to be 8. So 36 plus 8 is 36 plus 8. We're going to take that. I think that's 44. Let me verify on my, 44 grams per mole is how heavy. Now, this is propane again, C3H8. So, to do your percent now, we know we had 36 grams of that 44 was carbon times 100. And then we know we have 8 grams of the hydrogen of that 44 times 100. That'll give you your numbers there. And lastly, and then I'm done. Then we're out of here. Oh, it would have helped if I didn't cover up all those. Let's see. Oh my gosh. Okay, we've got 2 aluminums. So that's going to be 2 times 27, which is 54. Now we got to be careful. We've got 2 chromiums inside of the parentheses, but then out here we got 3. So that's going to be 3 times 2 is 6. And the chromium, when you look at it on the periodic table, weighs chromium is 52. So 6 times 52. Uh-oh, you know what? I made a mistake on my key that I was working on. So 6 times 52, let me make sure. 2 times 3 is 6. Chromium, double checking, because I don't want to miss, 52. So we're going to do 52 times 6 equals 312. Okay, and let's see. Now, we got 7 oxygens inside of the parentheses, but the parenthesis tells us we've got 3 of those. So 7 times 3 is going to be 21 oxygens. Each oxygen is 16. So 21 times 16 is, you know what? I made a mistake on my practice one. I'm going to make sure 21 times 16 is 336. So yay, now we've got to add these all up to find out what the molar mass of the whole thing is. 336 plus 312 plus 54. 54 equals 702 grams per mole. That's our total. So for each of these, we're going to be dividing by 702. Because we have 54 grams of aluminum total divided by the total. Then we got to do times 100 times 100 once we get the answer there. I'm not going to do the math for you now. You're going to do that. So there we go. Glad I caught this. And when I did my practice one, I said there were 5 chromiums. Duh, dummy me. 2 times 3 is 6 chromiums. All right, ladies and gentlemen, goodbye.